So whatever variables you're changing, you should maybe do like have a look at what their actual values are and see if it's the one thing back.
Almost scrolls down. Yeah.
Okay.
First pages.
I can
We don't have to.
Yeah.
This is
You
really
gotta
reference.
Yeah.
In the first page. That's why it's
Yeah, you also have to change where you right? It's a lot old one.
I've had this thing for like 5 years, and it went through the CS537 that I had.
You gotta set it for like when
It's
it's
great.
I mean, I didn't actually do this, so it might be easier said than done, but I think that was the idea.
Yeah, we set the users
No, I think my power
At the next page, but maybe Was there for SH like the shell? Is it the shell that's not starting?
the shell, I mean the
3 years.
the black box, like the 2MU that then starts.
Oh,
But when all the others like they said it was actually for the shell and so the shell
I mean, the computer's
like
weird.
so it's
Get a lot of
All right, let's get started. We'll wait due to some technical difficulties. But for P3B, we have put up the extra credit. The extra credit is going to be really simple once you have done the rest of the project. So the first extra credit thing is you create a new system called new exec, which specifies the maximum number of pages you can allocate to your stack. So remember that in P3B, you just have to keep growing your stack as it uses new pages, right? So in this extra credit, what you'll do is, based on this value, you will kill the process when it goes beyond a certain number of pages. So let's say this has a value of 2. When your stack grows to the second page, you kill the process. Okay. So if you've done P3B, this should be really easy. Another really easy extra credit is you're going to put an unmapped page between your code and your heap. So let's say your code starts at virtual address 100. If you currently access virtual address 99, that will go into your code region. Okay. So to prevent this, we are actually having an unmapped page in between. So if your code heap starts at 100, if you try to access 99, it will generate a fault. If you have done this part, wherein you created an unmapped page, this should be really easy. Okay, so assuming you get through the whole of P3B, this is like very easy extra credit to get done. Okay. Any questions in the extra credit? Okay. All right. I actually got a number of questions yesterday night about the null pointer thing, and most people were just like surprised that the code was faulting. Okay, so I'll show you how you can on your own debug a fault like that. I'm not going to give you the exact code to do the null pointer thing, but this should tell you how to debug when that happens. So remember that, let me just get one more thing working. Okay, remember that in exec, we are actually laying out the code sections, right? So we have this is the code section, and then we have the stack at page lines 52 to 54, and then beyond that will be the heap. Okay, so we want to modify it so that it goes beyond, the size doesn't start at 0 but starts at the first page boundary. Okay, so what I'm going to do is I'm going to show you what several people tried yesterday, and then I'll show you the problem it actually runs into. Okay, so we're just going to change size to page size. So we have offset the size of the process, the starting of the process from 0 to page size. Okay. The other thing that many people did do, but will still create a problem, is so your program no longer starts at 0, it starts at 1000 in hex, which is 4096. Okay. Do people remember why we do this? Here we are saying that your code section starts at some location. Previously it was 0, so it would go and check in virtual address 0 for the code of the program. But it's not going to be there because we've shifted it to the first page. Okay? Alright. So let me show you what happens. Alright, so our code does not work. So we have a CPU panic, and actually if you really read this through, it will tell you everything you need to actually debug this problem. Okay, what is it saying? It's saying we have a panic when we are starting SH, and then the panic is in copy UVM, and it could not find a page. Okay, so when you have a problem like this, the way to debug is just to go look at whatever code it's pointing out. Okay. So I believe this is where copy UVM is. Okay. All right. So let's go. I mean, if you stare at this for a little while, it will be really obvious to you what the problem is. Okay. For starters, here is where the panic is coming from. Okay. It's saying copy UVM page not present. So basically, it's looking for a page and it is not finding that page. Okay. And you can actually, it's really simple if you understood the rest of the code to understand why it is happening. Okay, it's starting from 0 and incrementing with page size, and then it's trying to copy over everything in the parent process to the child process. Okay, but what we have done is we have gone into the parent process and we have changed it so that there's nothing at 0. So the very first time it goes through this loop, it will try to access the first page, it will walk the page directory, and it will fail here because there is no page table entry for the first page. It will do a panic with the result that we saw previously. Okay, so when you're doing this project, it will be totally normal to hit panics everywhere. Okay, you have really two options. One is you put printfs everywhere in the code so that you don't hit that panic, you know exactly what's going on, and you do very careful sort of surgical modifications so that your code still works. Or when you do hit a panic or a bug, you trace it back to where it came from and you try to understand what's going on. Okay, so if you hit a panic or a page fault, don't freak out and email the list saying I got a panic. It's totally expected. Just read the code, look where it comes from, and you should be able to figure it out. Okay with me so far? Two questions. We'll go for you first.
So if you shift the I is equal to 0 to I is equal to page size, then it works.
You can try. Remember that this is all on video, so I don't want to give away the whole project on video, so that you can just like look at it and type it in. Yeah.
Hey, I wonder for the hour and you make the old address like start from the first page, no, from the second page.
Yeah.
Do you need to like kind of implement the view size also that page size?
Let me see if I understand what you're saying. So let's see that working. Okay, so we have alloc UVM, which is just allocating virtual memory for user space. What was your question in this?
I think it's that is like loaded loaded and you change the size like previously start from 0.
Correct.
And you just change it to page size.
Okay.
Yeah, that's the old size, right? So I just wondered if you need to change like the new size also to like also implement that.
I think I understand where you're going, but let me show you. So the size variable is actually storing the end of the page, right? So it doesn't really store, you don't have anything indicating where your process actually starts. Okay, so if you change this, you increment size by, everything that you do will just increment size. So starting from 4096, the rest of it will just keep incrementing size. So let's say you're just allocating one page, right? Previously it used to go from 0 to 4096. Because you've changed this, it will now go from 0 to 8192. The code that's already in here will just increment whatever size is already there. So you don't have to explicitly do it yourself. Okay. So there was another thing that people are making a mistake on that I saw yesterday, wherein like they were trying to get user init and user VMs like changed so that it would work. You probably can make it work like that, but it would be a lot of pain, and there is an easier way to do this. Okay, so if what you're thinking of involves changing user init and all those user first init process functions, there is an easier way. Okay, in general for this project, like there are like a million ways to go wrong. So you could do all sorts of hacky things to get it to work, but before you do that, try and think of like what would be the easiest way to do this, and then confirm that that wouldn't work, and then go on to the next idea. Okay, because it's really easy to spend all your time doing weird stuff in there that eventually does not work. Okay. So for the rest of discussion today, I originally just planned to yes.
Can I ask a question?
Yes, sure.
So this SC variable right now, you have our stuff that kind of lined up the pages like code and like that, and so the SC variable is like at the end of all that is, so that's where the stack operates.
Yeah.
But when we move the chunk of the stack to the bottom of the entire address space, does that mean the SC variable becomes the same size as the entire address space? Does it have to copy all of that?
No.
Or how does like the SC variable work? And will it copy the stack up all the way to the bottom?
Right. So the SC variable will be the cause of much misery in this project. So they're currently using it to track the whole process because they think it's a contiguous virtual address piece. Okay. In our case, it's not going to be so. So we have the stack alone, and then everything other than the stack you can still track with the size variable, the SC variable. Okay. So all of the places in the code wherein they're using SC to detect whether this is a valid access or not, you now have to do it in a different way. You need to have different variables to track how big your stack is, from where to where your stack is growing. And the code and the heap you can still track with SC, but you'll need some other additional things. Okay.
So when you do like a copy from here, you don't copy all the space in between like this and the stack.
Correct.
You kind of like copy the first and then tell the offset to the copy.
Yes. In fact, I don't think you can copy pages that have not been allocated or mapped. It would throw an error at that point. Okay. Any other questions? Yeah. Yeah, sure. So this is the function that actually deals with every different trap that you have. Okay. So there is a special case for a system call wherein you basically do the system call and then return. Otherwise, it has a switch case wherein you are actually handling all the different types of traps. Okay. So at the end, you have the default, which is what usually gets invoked when you have a page fault, because they're not handling page faults currently. So here, if you have a page fault, it will currently say it got killed. The trap number is 14, and then it was trying to access this address, and then you're killing the process. So what you have to do is you'll have to put another case for page fault, and in that within that case statement, you will have to handle the page fault. For the null pointer dereferencing, all you'll have to say in there is just segmentation fault, killing process, or something like that, and then it will kill the process. And that's the very easy part A of the project. For part B, you'll have to do slightly better than that. If it's a page fault that's in the stack, like you're just growing the stack and it creates a page fault, you'll have to catch that, and then you'll have to allocate that page, and then you'll have to return. Okay, so if you kill your process because it's trying to grow its stack, you'll lose points. Okay, so that's where the entire complexity is. The project. Any other question? Yeah.
So in this project, do we ever have to modify the instruction function?
The instruction pointer. it depends on where your page fault returns. So when you have a page fault, right? So what you want to do is you want to the page that it's faulting on, you want to allocate that page for your stack, right? And then you want to let that access continue. Okay, so I'd first do the project wherein you are able to figure out conclusively when the stack is growing, and then print that out. After that, you can handle whether you want to retry that instruction or not. Okay. Other questions?
How do you access the
So okay, let me see. Where is it kept? So basically the trap frame contains a lot of registers, which basically say where your process is currently going. Okay, and these registers have different meanings. For example, EAX actually means that's the return value on the stack. Okay, and if you look at exec, so if you look at this line 69, what they're putting is a spurious value on the stack that acts as the return value. So that's why you get a crash whenever you do return 0 instead of exit 0. Okay. So similarly, you have all of these registers here, and then the trap frame is what you use in order to access things like instruction pointer. Any other question? Okay. All right. So, and you guys know about cprintf by this point, I assume. Like, put cprintfs everywhere. Okay. Especially for this project, please don't just modify the code, let it crash in like weird ways, and then come to us. Okay. It'll be really hard for us to help you as well, right? So we need to understand what's going on in order to be able to help you. So look, put lots of printfs everywhere. That should really help. And you guys do know that we've extended well, not extended, but we've given you extra 5 late days. So we had a lot of people tell us that like with all the midterms that is going on for last week and this week, it's really hard to do the projects on time. So we've given you 5 extra late days, so you can use them as you want. And the way we're doing actually late days is you will submit your project, and then we will grade that project for you. And then at the end of the semester, you can look at the grade that you got on the project and then say, I want to use my late days on this project. I want to use so many late days on this project and so on. So you don't have to tell us beforehand like how many late days you're using for any project. It's up to when you submitted that thing. That's like how many late days you can use on a particular project. Make sense?
There isn't like a limit of how many late days per project. Like, you use all of your late days on one project.
You can, but the only exception is the last project. So P5B is due on December 12th, I think, 12th or 13th, and by 14th or 15th we have to hand in the grades for all of you guys. So we need all the project grades by then. So that is the only exception. Otherwise, you can use however many late days you want. Okay. Okay. Another thing that I saw during grading was many people do not understand what pointers in C. Okay, so we're just going to do a small tutorial. I'm going to show you what that means. Okay. So we have a pointer. Okay. So first, let's say I do something like this. So what does this mean? Is there a problem? Oh, still? Okay. I can actually do this. This one not going to be a lot of code. So let's say I do something like this, right? So is there a problem with this piece of code? Or basically, what is line 6 doing? Like, I'll give you options, okay? And then you can pick what option you think is right. So how many people think that the address of x, the address that x is pointing to, is being set to 100? Okay, so that's option A. Keep that in mind. Option B. Option B is I'm setting whatever the value, I mean, x is going to point to something, and then whatever value, let's say x points to y, for example. just to keep it simple. And then the value of y is now 100 due to this statement. Okay, so how many people think that's what's happening? Okay, good. All right. Another question. So if I do this, will it work? Okay. And why will it not work?
You're not setting the address, like you're not setting the access point to it. It's a mythology.
Right, exactly. So basically, this is just a pointer, okay? So it needs to point to something legal for us to do something like this. In other cases, like for example, if it did this, then it's kind of obvious, right? You're setting the value at address 100, address 0 to 100, but then there is nothing at value 0 because of the way we set up our address space, and so you'll get a fault. Okay, but then that will fault all the time. But if you do something like this, you'll still run into problems because you don't know what the value for x is at this point. Okay, so actually let's do that. Okay, so it is actually printing out nil. But this is very compiler and platform specific. So on other compilers, it could actually have had anything. Okay, it could have some arbitrary value, and then you're trying to change the value in that address. Okay. So let's actually do something like this. So now is this legal? Okay. So okay, all right. So what we're doing here is we're creating a variable on the stack. Okay, and then we're saying x points to that variable. Okay, and then we're just saying we're setting that variable to 100. So after this, if I do something like y, so it has the actual value. Okay, so this is the address of y, and this is the value of y. Okay. All right. And people do realize that y is on the stack, right? So it's not actually. So if you try to access y from any other context, it will fail. I'll give you an example for that. Let's see, y2. Okay. Actually, it is not just y2. Okay. So y. Okay, so can people see what's wrong with this? So we are saying we are allocating an address on this particular stack. Okay, so all your local variables or functions will be on the stack. Okay, and then we're saying we're going to return the address to that variable via foo. Okay, so far so good. The problem is that once you return from this function, everything on the stack will be deallocated. So y will just vanish. Okay, and here what we're doing is we are taking that address and we're saying we are actually going to print that value and then set that to 100. Okay, so you can actually see that C does give you a warning. It says function returns address of local variable. Okay, so this should be a cue to what's going wrong with it. So if you actually run the program, it will work, okay, but it will not quite have the value that you think it should have. So right now, it's just like the address that is returned by this is pointing to nowhere land. You're not actually changing y at all because y no longer exists. Okay? So if we give you a question like this on the exam, you should all be able to clearly point out that we're actually using the address of a local variable. It will go away when function returns, and so this whole program will be run. Okay. All right. Let's see. What other weird stuff can I show you? Okay, so okay, so how many people think this program will work? Let me ask it the reverse way. How many people think this program will not work? One person. For the rest of you, let me tell you what I'm trying to do in this program. Okay, I'm actually trying to use foo to initialize that pointer value. Okay, so what I want to do is instead of calling malloc in main, I'm just using foo to call malloc. So x is initially null. I'm just passing it to foo, and then foo initializes that pointer to some value. It does malloc. I mean, there's no cast, but don't worry about it. Or in fact, let me do a cast so that you're not thrown off by that. Okay, so we are doing a cast, and then we are printing the value and then setting the value. I mean, printing the pointer and then setting the value to 100. So let's do the take again. How many people think this will work? Hands up. Okay. How many people think this will not work? Not bad. Okay. For the people who, okay, let me just say that. I mean, why am I doing this as a contest? So this will not work. Okay, and I will tell you why it doesn't work. So we are saying that we are passing the pointer here, right? So we are passing the address of the pointer here. Okay, and then locally we are changing that value. So x doesn't actually change at all. So let me give you an example. So then, so since x is null, so we are passing in some value here. By the way, what does this mean? Ampersand x. Correct. So this, I know this is a little tricky, but it is the address of the pointer variable. Okay. So to do this in ASCII art, so we have x, okay, which is at some location, and it is pointing to something else. So currently it's pointing to 0. Let's say x is at 100, location 100. Okay. So now in function foo, let me show you a different function foo. Okay. Do people understand why this does not change the value of x? Do people understand that? We are passing in x by value. Okay. There's something called passing by value semantics. So here a copy of x is made on the stack, and then that's what foo gets. And when you're changing it to 12, you're actually changing the value on the stack. You're not actually changing whatever x was in your main function. Okay? So that's why we use pointers. So when we say this, what we're actually saying is that there is an address somewhere in memory which we want to change. Here is the address which is stored by x. When you say star x, go to the address that is inside x, and then you in that address put 12. Okay. So now, do you see why this will not work?
You want to plug into the
Right. So it's very similar to the same example. Okay. Here we are just saying. Here we're just changing the local value on the stack. Similarly, in that foo, we are actually changing the local pointer on the stack. Like the address is on the stack, and then we're changing it to point to something else. But then main will never see that change. Okay? So if we really wanted to change this, we would do something like this. Okay? And then finally we would say, okay, going through that line by line, this is a double pointer. Okay, so it points to the, so in our case, it points to the address of x. Okay, it points to the address of x. So we're saying, well, whatever is pointed to by this double pointer, put this address in that pointer. Okay. So that's why in here x actually changes because we're giving the address. Okay, just use it as a thumb rule. Whenever you want to modify something at an address, you need that address. Okay. Previously, when we were just sending x, it only had the value inside x and not the address of x. But now it actually has the address, and so it can modify x. Okay. So now. If we do this, so we actually see that this is the address of the double pointer. Okay, this is where it's stored on our local stack, which is why it has this huge value. Then this is the value that on the heap. That's what it returns from the function. Okay. All right. So in x86 code or in the other Linux code that you do, you will have to use pointers a lot. So you'll have to understand concepts like this. So what's an address, what's an value, and if you want to change something, do I have its actual address or am I changing it in its value? Okay. So one more question for you. So in here, we actually have the pointer x is on the stack, right? When you declare something in main, that's on the stack of main. Okay. But we are passing it to the function, and then we're able to safely use that value. Why is that?
Remember it's reallocated from
Right. Right. So for stack variables, or for any variable for that matter, think about the lifetime of that variable. Okay, heap variables have infinite life until the process basically until either that memory is freed or the process dies. That variable is going to be there. But for things on your stack, it's only until that function returns. Okay. Here we have declared it on the stack of main, but that stack is still there while you call foo, right? So that address is still valid. And when you return, that it's still there on the stack, so you can change it and you can reference it and change its value. So that's why this code example works. If you did it in the reverse way, it will not. If everything is in foo, but then you're calling it from main, foo would have gone by the time you return to main. Okay? Questions? Okay.
Is there a difference in the way you print out the pointer? Is there a difference between percent %p and
Percent p and percent x. So percent p, well, let's find out. There is. So basically, if you look at this, the last few bytes is what this is printing. Okay, if you do percentage p, it's showing you the whole thing. So it's just a matter of scope, I think, like how big your variable is. Okay. Any other questions? Yeah. Okay. If it's in the heap, then it's accessible from any function throughout the entire life of the program. Uh-huh. I see. Okay, that's an interesting case. Let's just do that. So the proposal is we do something like this, right? So in this case, wait. So if you do it like this, you would still need the address of the function. Okay. So whether it's on the stack or on the heap, if you want to change the value that the pointer has, then you need its address. It doesn't matter whether it's on the stack or the heap. Okay. Here, all you're declaring is a single integer pointer. Okay. If you instead had it like this, okay. I know this is becoming very starry, but if you had it like this, then you wouldn't need the address. Because by definition, it's a double pointer. And then you are only accessing the value inside the pointer. Right? Star x would be the address that you want to modify. So then you wouldn't need it. Okay? Do people understand that? Okay. Any other questions? Okay. Yeah. So let's see. So let's say we have y2, then this prints foo. Then you have void bar, this prints bar. Okay. Now these functions have the same signature. So you could have a function pointer which points to either of them, and then just access the function pointer and thereby get it to work. Okay. So okay. So it's been a while since I did function pointer, so I'll probably mess up. First, let's try this. Okay, so do you see this is the address of the foo function? Okay, so okay, this is very nice. So 504 is where foo is stored in memory, and then 514 is where foo is actually stored in memory. Okay, so these are the addresses of the functions itself. Okay, so let me show you. Okay, can you see the thing in assembly? So at 504 we have foo. At 514 we have bar. Okay, so in order to access a function, the things that you really need to know are where the function is in memory, what it returns, and what its arguments are. Okay, because like think about it, like when you're actually doing this, what are you doing? You're pushing the current value there, and then you're basically calling put s, right, inside that function. I mean, this function basically doesn't take any pointers, so there's not much to do. But if you had pointers, you would access them from the stack of the function. Let me show that. Yeah, I do have it actually. Okay, now you can see that foo and bar are much bigger, right? Because they're actually doing something which relates to the stack instead of just like printing something. So you still see that there is the printf function. Okay, we do call printf there, but before that we are actually accessing something with relation to where the stack is. Okay, so all of this stuff that you're seeing is basically to make sure that like you are setting up the correct parameters to call printf, right? Because printf is another function, and printf expects that you give it certain parameters so that you can print that stuff out. Okay, so you need to set up all of these things, and it just assumes that there are things that are there on the stack. Okay, so here when you have different parameters to foo and to bar, it will look for those things at the current stack address. Okay, so you need to know how many arguments there are, how big each argument is, in order to actually effectively perform that function. And you need to know what to return. So if you have all of those things, you can actually call any function. So, and that's what a function pointer actually does. It doesn't need the name if it has the address of the function. Yes. So trying to remember how I use function pointers. Yeah, actually I can't remember off the top of my head. So I'll have to go look it up. Well, I'll give you pseudocode. Even if it doesn't compile, it looks something like this. Okay. So what you'll say is voids. This is not visible, I think. So let's look it. So you'll say something like void star f pointer, which takes an int equal to ampersand. Okay, so this is a pseudocode for a function pointer which may not compile. But what you're saying is that there is a function. Wait, why am I saying void star? There is a function that basically returns nothing and takes an int. Okay, and then that function is present at this address. Okay, and so when you are actually calling the pointer, you'll say something like this. Okay, so what we're basically saying is that whatever is in the address of like f pointer, I want to call that function, and the argument that I want to give it is 12. Does it make sense? So this is just like calling foo of 12, but then you're using a function pointer to do that. Okay. So the reason that you need the return type and the argument list is so that the compiler can check. Okay. For example, if you do something like this, it's expecting a pointer but you're not giving anything. The compiler can now tell you that you are calling it wrong. Okay. So that's why you need the type, the argument list and the return type for the function. Okay. Any more questions? Okay, if you don't have any more questions, we're done for today. Thank you.